Hi everyone, it's Mrs. Griffin with the Unit 4 Lesson 6 video. We're going to talk about going beyond CPCTC. So we spent a lot of time using more and more complicated givens to end up proving triangles and pieces of them are congruent. But now what we're going to do is use our proof blocks backwards, where I'm going to be able to tell that things are congruent, usually from CPCTC, and that will lead me towards knowing something new about my figure that was not provided earlier on. So for example, number 1, we know that XYRS is a rectangle and that XM is congruent to SM. So I'm going to mark those things off. XM is congruent to SM. And since I know it's a rectangle, there's a lot of properties I can use. Hopefully you're seeing these two triangles appear congruent and that those are the two that we should kind of stick for, because the other third triangle there is not the same as these two. And these two are using XM and SM as sides. So thinking about what else we know about a rectangle, because that's our other given, I know that they have opposite sides congruent. So I'm going to write that XY is congruent to SR, and that's giving me another side pair. Now, there's no point in talking about XS being congruent to YR since neither of those is a side of the triangles I've highlighted. So let me come up with another property about rectangles. I know that they always have all right angles, and that allows me to mark off an angle pair in these pictures. So I have all 4 congruent right angles. I only really care about angle Y and angle R, and so they are congruent and they equal 90. And I need to have both here because now when I go to look at the triangle situation here, this looks like 2 sides and an angle. Remember, that's that donkey theorem, and we don't want that. But also remember that if you see that donkey theorem, a special case of it is HL, when we have a right triangle. And since we do have right triangles here, we need to say that so that we can use the special case. So right triangles have right angles. And I want to say that triangle XYM and triangle SRM are right triangles. Because if I don't say that, then I'm not allowed to use the special case of SSA, which is called HL, because you only have a hypotenuse and a leg if you have right triangles. And so now that I know I have right triangles, I know their hypotenuses are congruent from the given, and I know their legs are congruent because of the rectangle. I know they're congruent triangles. Now, always after our triangles be congruent, we've been talking about CPCTC. CPCTC lets me pick a different side or angle pair to be congruent than the ones in the given. What I need to do now is kind of plan ahead, because what I need to pick for my CPCTC is not told to me, but it's telling me that whatever I pick for CPCTC is going to be used to show that M is the midpoint of YR. So I need to use CPCTC to pick things that would mean that M has to be the midpoint of YR. So from my green and pink triangles, I'm going to pick the fact that from CPCTC, YM has to be congruent to MR. And the reason I'm saying that is because if I know that those are congruent, that means M has to be the midpoint. And I know that that's true because a midpoint divides a segment into 2 congruent segments. I just know it backwards. I knew I had 2 congruent segments, which means I have to have a midpoint. So I went from knowing they were congruent segments to knowing it had to be a midpoint. I've used the block backwards. Number 2, we have another quadrilateral. We have a parallelogram, and we know that RE is congruent to PD. We need to prove SQ and DE bisect each other. So what I need to do is figure out triangles that can end up congruent from the information in my given. There's a bunch of them, but I want to pick ones that are going to have pieces. So I'll be able to show SQ and DE bisect each other, meaning cut each other in half. So like I need to pick these 2 triangles so that I can use the pieces of SQ and DE. I don't want to use the whole SQ and DE. I want halves of them because the bisect cuts things in half. All right, so in that case, knowing RE is congruent to PD doesn't really help me here. But if I account for the fact that this is a parallelogram, SR would be congruent to PQ, and then I could subtract RE and PD and get the pieces I actually need for the highlighted triangles. So I'm going to talk about the fact that parallelograms have opposite sides congruent to say that SR is congruent to PQ. That way, when I take the SR and subtract off the portion between R and E, so here's SR, if I subtract off the portion between R and E, what I'm left with is SE. And when I take PD and I subtract it from PQ, that whole thing, what I'll be left with is just this section between D and Q. So I'll have DQ. And now, because I took equal things away from equal things, I'll have equal results and that subtraction. Now I actually have a side pair in my triangle picture. Continuing from there, I know that opposite sides of a parallelogram are also parallel. So not only are SR and PQ congruent, but they are parallel. That's handy because parallel lines form congruent alternate interior, corresponding, etc., etc. And if I look here, I'm seeing alternate interior angles with that Z. So I can use angle 1 and angle 2 and say they're congruent because of the congruent alternate interior angles. So angle 1 is congruent to angle 2. Now I also see vertical angles. I'm looking at this bow tie pattern happening here with angle 3 and angle 4. And so I can say angle 3 and angle 4 are congruent because vertical angles are congruent. And that means that that pink and green triangle has to be congruent using angle side. So SET has to be congruent to QDT. Now, after the congruent triangles always comes CPCTC, never anything else. The pieces that I'm going to use are going to have to end up leading me to SQ and DE bisecting each other. So not just one bisecting, but both of them. That means I need to use ST and TQ being congruent, along with DT and TE being congruent. I need both. This pair and this pair. So many tick marks, it looks like a comb. All right, so I'm going to use CPCTC to say ST is congruent to TQ and DT is congruent to TE. That way, I'll be able to say, well, all these pieces are congruent. That means SQ and DE must be bisecting each other. I'm going to use EO for each other because segment bisectors divide segments into two congruent segments. And for each one of those, I'm showing I do have two congruent segments, so I must have a bisector. So again, we're working backwards. We know this to get that. All right. For number 3, BD is a median and it's an altitude to AC. That means we're going to use both of those terms to help get me some information about this picture. So first off, a median connects a vertex to the opposite midpoint, which means that D is the midpoint of AC. And then we do our midpoint definition to say the next step. And then because D is the midpoint, we now know AD is congruent to DC. Next, we're going to talk about the fact that we have an altitude. So I'm going to write the altitude definition. And since an altitude goes from the vertex perpendicular to the opposite side, BD, the altitude has to be perpendicular to AC. Now, knowing that perpendicular lines form congruent right angles, I'm going to have two angles that are congruent right angles there. Perpendicular lines form congruent right angles. And angle 1 is congruent to angle 2, which equals 90. From there, I'm noticing these two little triangles are both sharing BD, so I'm going to use reflexive to say BD is congruent to itself. And now I know that these two little triangles are congruent to one another by side angle side. So triangle ABD is congruent to triangle CBD. Next has to be CPCTC. So what we need to do is look at our prove statement. We're trying to prove this is an isosceles triangle, the big one. So the pieces that I pick for CPCTC need to show that that's true. So I can choose to either pick the fact that AB is congruent to BC, or I could have also done A being congruent to C, because either of those is going to show that this is an isosceles triangle, and I know that those things are now true because my little triangles are congruent. So because I found that from CPCTC, I know that triangle ABC has to be isosceles. And I know that because isosceles triangles have two congruent sides, or you can use angles if you use the angles here. Doesn't matter, either one. All right, for number 4, CD is an altitude. So again, we're going to define altitude. It goes perpendicular. And so CD would end up perpendicular to AB, and then we get our perpendicular lines to form congruent right angles. And that would make angle 1 congruent to angle 2, which would equal 90. We also know that CD bisects angle ACB, so up in here we would know that 3 and 4 were congruent because of the rule for an angle bisector. We're bisecting an angle to get two congruent angles. And we also have the fact that they're sharing CD, so it's reflexive. And now we have that our triangles are going to be congruent because I'm looking at an angle side angle situation. So my triangle ACD is congruent to triangle BCD. After the triangles always has to be CPCTC. Now I'm trying to pick something that's going to show CD as a median. So CD would be a median if D was a midpoint, and D would be a midpoint if AD was congruent to DB. So AD is congruent to DB because of CPCTC from those triangles, which means that D is a midpoint of AB, because a midpoint divides a segment to two congruent segments, and that's exactly what just happened by those being equal parts. And then finally, CD must be a median because it's going to a midpoint, since I now know that D is a midpoint. And it's going from a vertex to the opposite midpoint. All right, number 5. We have that BA is congruent to BC. We have that BD bisects angle ABC, so that would make these two parts congruent, 1 and 2. So I'm going to use that first. Remember that segments can be equal or congruent, kind of means the same thing. All right, so angle 1 is congruent to angle 2 because of the angle bisector. And an angle bisector divides an angle into two congruent angles. All right, next, we could do a few different things. I'm just going to use BD as reflexive because it's pretty straightforward. All right, now we have our triangles now congruent by side angle side, and we'll follow that up with CPCTC. And we're focusing on how to show that BDC down here, BDC is a 90-degree angle. There's actually 2 of them, so I'm going to focus on both for a moment. If I talk about how they're congruent using CPCTC, that's one thing. I'm going to call them angle 3 and angle 4. That just means that they're equal to each other. I also happen to know that they're supplements because 3 and 4 form a linear pair. They are a linear pair. So if you think about that, if they're supplements and they're congruent, they have to be right angles. It's not an official proof block, but it makes sense. So BDC has to be 90. Angle 3 and angle 4 are both 90. All right, I'll see you in class.